Before we discuss the dot product, I want to briefly discuss what I refer to as unit vector form. This might be a slightly different way of expressing a vector than I'm used to talking about in a math class. So I want to make sure I'm clear on what I mean by unit vector form. So vector A can be split into components, an x component, a y component, and a z component. Often the z component is 0 because the math that we do, we don't want to add an extra layer by adding a third dimension. It's unnecessary. So a lot of times we're just working in the x and the y, but sometimes we will get into the z direction. So I want to make sure that we discuss this existence. In a math course, you might have seen this as I, J, K. I'm used to doing x, y, and z because in physics, we are talking about the actual x, y, and z axes. So we're trying to express three-dimensional space or three-dimensional form. So we want to be able to talk about going in the x direction, not going in the I direction. So when we talk about these unit vectors here, x hat, y hat, and z hat, they have a magnitude of 1 and they're just expressing the direction. And then this would just be the component. So another way of telling you what a vector is to just give you the x, the y, and the z component rather than giving you the magnitude and direction. You can get magnitude and direction back by using Pythagorean's theorem and inverse tangent, though that gets a little bit more complicated when you're dealing with 3 dimensions rather than just 2 dimensions. Alright, so now let's talk about the dot product. The dot product is the magnitude of A times the component of B in the A direction. So effectively what we're trying to do is set up and multiply together just the portion of the vectors that are parallel to each other. Because we're going to have vector A pointing off in some direction and vector B pointing off in some direction, and there's going to be an angle between them. And what we're trying to set it up is so that we take the magnitude of A times the portion of B that is essentially on top of A. So we're going to take the magnitude of A times the portion of B that's headed in the same direction as A. So we want to multiply it together two portions of a vector that are parallel to each other. And we have 2 ways of accomplishing that. One is to literally use the definition. We're going to take the magnitude of A times the magnitude of B times the cosine of phi, where phi is the smallest angle between the 2 vectors. So essentially we're finding the component of B that is along the same direction as A. The other way to do it is to use it in more of a unit vector form, where we're going to multiply the x components together, the y components together, and the z components together, and then add them all. And the reason why this works is if you look at the unit vectors. So x hat dotted with x hat equals y hat dotted with y hat equals z hat dotted with z hat. And the reason why this works is, remember, the unit vectors have only a direction. So their magnitude is 1. So when we do the magnitude of A times the magnitude of V in terms of what their unit vector is, if they're an x hat, a y hat, or a z hat, you're going to be taking 1 times 1, and then the angle between them would be 0 because y is in the same direction as y. So you get that the dot product would be 1 for those particular unit vectors. So which is why you get this. You're just multiplying together the x terms, the y terms, and the z terms, because the x hat and the x hat that would have been with this component of the vector and this component of the vector, you would have dotted those together and just ended up with 1. Same thing with the y. The y hat dotted with the y hat is 1. The z hat and the z hat that would have gone with these components of the vector, when you dot them together, you just get 1. So you only have to worry about the components of the vectors to multiply together then. On the other hand, if you had tried to take the dot product of the x term and the y term, or the x term and the z term and the y term and the z term, in this case, once again, the magnitude of those unit vectors is 1, so you're just taking 1 times 1, but now you're doing the cosine of 90 degrees, because the x component would be to the right and the y component would be up. Those are 90 degrees from each other, and so the cosine of 90 degrees is 0. The unit was 0. So you'd be taking a of x times b of y, but then you're multiplying by 0 because when you dot the unit vectors, you end up with 0. So that's why you don't have to worry about anything that isn't in the same direction. So you don't have to worry about multiplying a of x times b of y because the result would be 0. Due to when you dot the unit vectors together, it gives you 0. And the answer that you get when you do a dot product is actually scalar. So you're dotting two vectors together, but then the answer that you get in the end is going to be a scalar term. So that really matters in physics because some of our quantities are scalar and some of them are vectors. So you have to make sure that when we're taking a dot product, we're dotting together two vectors and that our answer is supposed to be a scalar. Otherwise, the technique doesn't work.